Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, thank you, Peter. So today I'm going to be talking about market design. And so as you might expect, something with the title markets in it, market design is something economists are interested in quite a bit. And vaguely can be described as anything where there's some good or object to be allocated and there are people with interest. So the notion of markets is quite broad. And one market that economists have looked at a lot is the market for assigning school children to schools in, for example, large cities in the United States. So up here what I have is a page from a pamphlet given out by the public schools in the city of Boston to parents. Different meaning of public schools than I think you would have here. And you'll see, it starts out by right away leading to parents by describing that assignments are going to be made by a computer programmed with a mathematical formula. And by the way, the bolding is theirs. So this is what the city of Boston chose to emphasize. And then it goes on and it describes basically the algorithm that's used in the market to assign children to schools. This is another pamphlet from the city of Rochester, and again, it starts out by talking about a computerized placement system, and says the computer has a database and it assigns people a number at random. So it's talking about random numbers in the pamphlet to parents. And then it goes on and describes what actually turns out to be a different algorithm. So even though sort of all these markets are out there in the world, over time computers are more and more taking over these markets. And fundamentally, underlying many of these markets, there are interesting algorithmic questions about what the best way to structure these markets is. And it's not just sort of markets out there in the world that are getting taken over by computers, but we're sort of creating new sorts of markets all the time that feature things. So there's the obvious markets like the markets for internet advertising. Companies are creating their own currencies that create a marketplace of their own. So Facebook credits, I view Microsoft Xbox Live points as creating a new marketplace. And then things that might look less like a traditional market. For example, many peer-to-peer systems create marketplaces of one sort or another. Stack Overflow creates a market where people are rewarded for answering each other's programming questions in terms of reputation and points. So there are sort of a wide variety of markets that people within computer science are creating as well. So I've looked at quite a variety of different markets in my work. Today I'm going to talk about two of them. So the first piece of work I'm going to talk about is some joint work through Ron Murdy and David Parks about spectrum auctions. And I'll get into more details on that in a minute. And then in the latter portion of the talk, I will talk about a measurement study of peer-to-peer file sharing community, and that's joint work with John Lai, Haji Zhang, and Aviv Zohar. And please feel free to interrupt me at any time with questions.
So would you say Foursquare is also creating a market? It's selling limited places to people on my issues.
Yeah, so I could see that. I could certainly fit that in within the realm of things I would be interested in and view it as a market. Yeah, I mean, so markets definitely do not have to involve money, or they can involve money it's not actual money, that's some sort of artificial money. And in fact, in the second portion of my talk, I will be talking about something where there's no actual money involved, but we view there as really being money in the system. Okay, so suppose you want to deploy some sort of application that requires access to wireless spectrum. And so one thing you can do if you're sort of a big player like television or a cell phone company is you can get what's known as licensed spectrum, where basically you own the exclusive right to use some range of frequencies over some large area, and no one else is allowed to be using the spectrum you have. So you can provide very good sort of quality of service type guarantees. On the other hand, right, you are the only person, and so that might restrict how many other new devices could use that chunk of spectrum. So if you're not one of these big players, your option is to use what's known as unlicensed spectrum, where basically there are some minimum requirements set up by government regulators, but for the most part, you can use it to a wide variety of things. So this is where, for example, Wi-Fi operates, but it's also where car alarms and microwave ovens and all sorts of other things operate. So you have to deal with the possibility that you're going to get interference in this, this spectrum. So to give you a sense of how the balance of the spectrum allocated, so this is a map of how the spectrum is carved up in the United States, all of the applications that you can use it for. So the details of all the applications aren't important. Sort of just to give you a sense of where these two things stack. The bulk of it, that's sort of nice brownish yellow color on this screen, is the spectrum that's allocated for license use, and these smaller greenish portions are the areas that you can sort of deploy some new device in. That's sort of all you have to work with. So everyone who wants to deploy something new has to compete for these small areas.
There's just one dimension here, which is frequency, right?
It's just yeah. Otherwise, I run out of. And so it turns out that a lot of this licensed spectrum is owned by somebody, and they have the exclusive right to use it, but they're not using it, or not using it all the time. So this is some measurements that were done in Chicago in 2005, and black areas are where they observe the signal that seemed to indicate that somebody's using the spectrum, and white areas where it seemed to be clear and it could be used for some other purpose. And you can see the huge parts of the spectrum in sort of, this is in TV bands, are available. And I've just sort of marked some of some entire channels in red that are available either pretty much all the time or in the case of this one, for at least part of the day that could be used for some other purpose. So there's all this incredibly valuable and useful spectrum out there that is owned by somebody, unused, and devices can't take advantage of it. They're forced to contend for this limited amount of spectrum. So people are aware of this, and there have been proposals. You might have heard of white spaces and sort of other dynamic spectrum access technologies, where the proposal is, we know that, especially in these TV bands, not all TV channels are used everywhere, so we should free them up and create rules for Wi-Fi-like devices to operate because, for example, this allows you to pass signals through walls significantly better in some of these frequencies than in the typical Wi-Fi frequencies. Right, so people have looked at it and said, okay, well, the places I've marked in blue are the ones that are allocated to over-the-air TV broadcasts in the United States, and so some of those are frequencies that might become accessible in some locations to this sort of access pattern. But you can see still the huge, vast majority of spectrum is still not covered. It's still locked up in this regime where it's licensed to particular people for particular purposes. So if you want to deploy some sort of new application and you want to get something like these licensed guarantees, you're kind of stuck. So you can participate in occasional auctions that are run by government regulators, the FCC in the case of the US, and they'll take some chunk of that big spectrum I've outlined before, carve it up to channels, and sell it. And so in the last big round of auctions in the United States, you could buy a license, for example, that might cover the entire United States for a chunk of frequency. Or the smallest you could buy carve the United States up into about 700 pieces. So basically a major metropolitan area is the smallest scale at which you could operate in these auctions. So unless you have millions or billions of dollars, this is not something that a market that you can participate in. On the other hand, there's all sorts of devices out there that might benefit from being able to access from some of this unused spectrum. It's pretty easy to set up your own low-powered TV station. You could try setting up, many people are interested in set up sort of municipal Wi-Fi networks that could potentially use some of this spectrum. Delay-tolerant network type applications could potentially use this spectrum. So there's a lot of smaller scale, more local applications that could potentially benefit that don't necessarily need or want the right across an entire city or an entire country. And so there's been a line of work looking at how we can design auctions to sell spectrum both more locally and on a more dynamic basis. And so when we're working on these lower scales, we can't just rely on the fact that we're carving up countries into a small number of pieces to deal with the interference issue. we have to explicitly think about who interferes with whom. And people usually do this through a formalism known as a conflict graph. So each node on this graph is some application that wishes to use spectrum. And there's an edge between two nodes if they would interfere with each other, if they were to both try to broadcast at the same time. And I've colored a set of nodes blue that might be ones that are selected as winners of some auction or other mechanism. And you'll note that I've chosen an independent set. All right, so this provides a nice guarantee that none of the winners will interfere with each other. They'll all be guaranteed to have a free channel on which they can operate. The downside of this, though, right, is that you might have like situations like down here in the corner where one guy is preventing 3 other guys from being able to get any access to spectrum. And this might be inefficient, right? There are various laptops floating around the room, and we don't have a rule that only one person's laptop can be operational at any given time. In practice, we have a Mac, and that Mac allows multiple contending devices to be able to use the same chunk of spectrum, and they basically have a protocol to share the available spectrum. And so one of the things we believe is that this sharing is valuable in other applications. Many devices are out there that can use Macs, and so we wanted to see, can we take some of the work that's done in this space and figure out how to design auctions and design an auction that's going to allow sharing, and sort of how much better is that going to allow us to utilize available spectrum? Questions so far?
So there's a kind of technical question, which is, how do you make sharing possible at all? And you're then saying there's an economic question that, assuming you have the technical means to allow sharing, how do you best allocate what you now have?
Yeah. Yeah. So in this we have an underlying model and abstract away sort of the details of how the Mac deals with the sharing. That we use a particular model in the paper, but in some sense, much of the work we do is economic, and that's sort of a modular piece that you could swap out a different model of how.
So why is the economics any different than if it was not shared?
The major reason, which I'll talk about a bit, is basically once you start sharing, you no longer just care about whether or not you get a channel. Now you start caring about with whom you share a channel. Right, and so that introduces what in auctions are known as externalities, and suddenly the auctions become significantly more complicated because now it's not just a simple binary decision about whether you're allocated. Now you have to do these sort of.
Well, you might want to bid $100 if I'm in bed with him, but only $50 if he's allocated. Exactly,
because now what they're doing is going to affect you. And there's been a lot of work on these sorts of auctions, most of which just takes the easy approach and says we're not going to allow sharing. One particular piece is an algorithm called Veritas that sounds like it should have been come up with by a bunch of Harvard people. But actually it's some people at UC San Diego. And so I'll come back to that later as sort of a benchmark to compare our work against. And then there's been a little bit of work that's chipped away sort of at the edges of sharing. So maybe allowed sharing in simple scenarios where I am a cell phone company, I want to sell off the right to be a secondary user when I'm not doing it. And you know my usage pattern, so you can figure out what that's worth to you, but the participants in the auction won't share. There's only going to be one winner. And then there's been some work that's come up with very general model, but because if you allow people to sort of express arbitrary preferences over whom they share with, you get an intractable optimization problem to deal with. So the way we manage to get something that we can work with these externalities is we give a sort of simple preference language where people can express their preferences. So we allow them to express a wide variety of things. We allow them to talk about whether or not they can use a Mac. So some applications may not be able to use a Mac. They might need exclusive access in their local area. They might not need all of the bandwidth available in a given channel. They might need only like half the capacity of a channel. They might not be transmitting all the time. They might only have data to send 10% of the time, and so the rest of the time they don't care. Someone else can be using it, and they might have some valuation for it. So we can sort of describe a particular application in terms of this profile of what it wants to do, and then the way we're going to get something tractable out of it. Question?
Yeah. So I want to understand what the difference between half a channel and 10% of the time. So in terms of your plot, does half a channel means half the width, and 10% of the time means 10% of black stripe on On the y-axis?
Yeah. So you can look at it that way. So it is something of a question of time scale, right? If you get down to a small enough time scale, the two of them do look the same. And so we're thinking of these auctions as being sort of run on a medium or longer time scale, where indeed there is this meaningful separation between the two axes. And so we have an underlying stochastic model that sort of can take this information about usage patterns and distill it down to the question of, for each person, what fraction of the things that I wanted to send am I going to get to send, right? So that's what I really care about. At some level, I don't care about exactly what other people are doing. I want to know how it's going to impact the amount of my demand I get to have satisfied. And so if you know some auction theory, basically what this is going to let us do, this stochastic model is going to let us work in a single parameter domain space that's going to allow us to leverage some techniques from there. Other questions about the model? Okay. Right, so now that we have this model, right, we can set up an optimization problem. So we'll assume that people have the same sort of usage patterns, and they only differ in terms of whether they can share or demand exclusive access for the purposes of this example. So I've marked the nodes up here with an S or X, depending on whether they're capable of sharing or they want exclusive access, and then their valuations. And so now we have an optimization problem to figure out what is the best set of people to choose to allocate, given this model.
Treating the AI as actual randomness.
Yeah, so one simplification of the model is we assume that you sort of, if you think of carving time up into a bunch of periods, your IID, it's the IID probability you're active in each period, which is definitely a simplification. And so that's one of the things, you could put a richer model of how this works as long as in the end you can reduce it down to a single parameter.
So the graph means you can share with your neighbors, but not with anyone else.
So the graph says if you allocate me and my neighbor, then we will interfere with each other. So if you allocate me and somebody who's not my neighbor, I don't care because I'm not going to do it. And so this is a simplification as well, right? Interference is not actually binary. It means you're at some threshold and it's actually additive, but so this is, I guess, a standard representation that abstracts at least some of that away.
And you assume if they share, all those that are linked with, they cannot have more than 100% of access, right?
Right. Yeah. So that's the underlying stochastic model I mentioned goes and solves that, figures out based on a simple model of how the MAC is going to work, how much access you're going to get when people are trying to contend at the same time.
What's the difference between X and D equals 1, A equals 1?
So D equals 1, A equals 1 says I have data to send all the time, and I would like to use the full capacity of the channel.
Sorry,
but if I'm
same as exclusive access.
So that says I would be happiest if you gave me a full channel to myself. But if I'm capable of sharing, maybe I can still do something useful, even if you only gave me half of the bandwidth I might like in an ideal world.
Oh, and the X guys say
the X guy says
goes to 0.
Yeah, exactly. And right, so now we have an optimization problem to solve. And so one observation about this: if everyone in the world demanded exclusive access, we'd be back in the independent set world, right? And so we know we can't solve that optimally. So in many independent set type problems, greedy approaches are a reasonable heuristic. In some cases, you can give approximation ratio bounds on them. And so we're going to use a greedy approach to try to solve this optimization problem. And sort of the way greedy works in this setting is we look at the person who's expressed the highest valuation for a spectrum. So that'll be this guy up here who has a value of 12. And we say, great, we can allocate you. And then we move on to the person who has the next highest valuation. That's this 11. Next to him, we say, well, you want exclusive access. And we can't give you exclusive access because we already allocated your neighbor, so we can't allocate you. So we go on to the guy with the next highest valuation, and he wants exclusive access, but none of his neighbors have been allocated, so that's fine. And we continue on in this greedy fashion until we finish allocating. And notice here, now we've ended up down here with a bunch of people sharing because they're capable of doing so.
And just so if you have two neighbors and let's say they both want, half a channel half of the time. I mean, if there was actually probabilistic behavior, you would have interference a quarter of the time, right?
Right. Yeah. So our model does actually have a term where you sort of have to sum over the various activation patterns. You know, what's the probability that I have both neighbors active? What am I going to get in that case?
Yeah. So what do you? Just to be clear, the optimization problem you're solving here is just to maximize social welfare.
It's maximize social welfare. Yeah.
And so, how do you count when you have two neighbors share and there's some non-zero probability of interference?
Right. So in that case, right. So if they're all capable of sharing, we assume that they split up the available capacity, so they don't all have their demand fully satisfied. We assume that people are sort of quasi-linear in the amount that you give them. And if somebody requires exclusive access, then actually in the...
I'm sorry. So if both of us want half a channel half the time, let's say.
Yep.
And then we're the only ones talking about sharing this particular channel.
Yep.
Then you basically assume that you can sort of assign a schedule in which we don't interfere at all.
Yep.
So then it's not, then I shouldn't think of the AIs as probabilistic then, right?
So the D's are how much of the channel we want. The A's are what portion of the time we're going to be
So I'm
active.
just talking about the A's here, right?
Okay.
So if the A's were actually treated as probabilities, then if AI and JJ are both non-zero, then with probability AI, AJ, you have a conflict.
Yep.
But you're basically saying, no, you don't look at it that way.
No, we say you do have a conflict, but if you're capable of sharing, you can sort of split. So you have a conflict, but you'd both like a whole channel.
Okay, so suppose we both have D equals 1 then, and then AI and AJ positive.
Right. So you
basically there would be a term AI AJ which got 0 utility.
It wouldn't be 0 because we're still giving you some bandwidth, right? You'd like the whole channel, but if you can share, you can use half the channel. There is a term, if there's an exclusive guy, right there, you are getting 0. And we actually allow you to incorporate a penalty term for disconnecting people, right? Because some applications might be...
You're allowing interference.
Yeah.
And it just gives diminished utility.
It's diminished utility
to kind of the wasted demand.
Exactly.
Okay. I get it.
So in this graph, why is it better to allocate the 10x on top and not the 5 and 7s right below it?
It
right?
might well not be. We're running a greedy algorithm, right? So there's no guarantee of optimality for the greedy algorithm.
Just on my point again, so the value is what I would get if I have the whole bandwidth for that channel. But the decrease in it is linear in the interference probability.
Yeah, that's the model we use. You could incorporate a different model.
Yeah.
What about the algorithm where you take all the S's, all the connected components with S's, collate them?
Yeah, so we haven't looked too much at other algorithms. And you'll see
treat them as one big node with the sum of the utilities.
So there's, as I'll get to in a second, there's actually some constraints on our algorithm design, and there's a reason we like the greedy approach in terms of constraints on our algorithm design. So you might be able to do something like that. We just sort of went with a simple, because it's been used in previous sort of work in this space. Okay, right. So thus far we've been talking about this optimization problem, and we've said, yeah, so we know all of these values that people have, right? But in practice, we're going to have to ask people, what is it worth to you to participate in this application? And they might not necessarily be willing to tell us, right? They're out for their own interests. So I'm going to take a brief digression into some basic auction theory to sort of illustrate this point. So suppose we have Bart and Lisa, and we like to decide who's going to get to own this Xbox game. And we're going to do it by using what's known as a first price auction, where each of them is going to name an amount of money that they're willing to pay. And whoever names the larger amount of money is going to receive the game, and they're going to pay whatever amount of money they named. Any questions about how it's going to work? Okay. So suppose you're Bart, and you think that this game is worth $40 to you. What should you say in this auction?
One more than what you think she's going to say.
Yeah, right. So it's a bit of an ill-formed question, right? You would like to win the game as long as you don't have to pay more than $40 for it, but you'd like to pay as little as possible. So you have to have some model of what it is Lisa's going to think the game is worth. Maybe you think her value is drawn uniformly at random from between 0 and 60 or something like that. So you right, so you have to do this sort of reasoning about what other people are going to do to figure out what you should do. And maybe, after that reasoning, you decide that maybe the right thing for me to do is bid $20 or some other amount. And so you can do, so sort of the techniques for doing this this analysis, this is formally sort of people are looking for a Bayes-Nash equilibrium in the economic sense, so the sort of known techniques for figuring out what you should bid given a model of what you think the other person's valuation is. But you do have to do some reasoning to figure out what it is you should do. So let's change up the way we're going to run the auction a little. So we're going to do everything the same except when it comes to charging money. And the change we're going to make is instead of charging you the amount that you bid, we're going to charge you the amount that the other person bid, or the second highest valuation. It's called a second price auction. Right, so now in the same setting, it turns out that the optimal thing for you to do is to just reveal your true valuation. Right, so you don't need to do this reasoning about what the other person's valuation is. You just figure out what it's worth to you, and you say that, and that's guaranteed to be optimal. So this is the property known as strategyproofness, and it guarantees that no matter what strategy the other person uses, it's going to be optimal for you to make a bid that is your true valuation. And this has sort of a number of benefits when it comes to designing an auction. So one benefit is it creates strategic simplicity for the participants in the auction, right? They don't need to do complicated reasoning about how their bids are going, how they should bid based on how others are going to bid and who exactly the participants are. They just have to figure out what it's worth to them and then announce that. Another nice benefit is it provides some stability in what you report. So sort of one of the things that turned up in the early days of internet advertising for auctions is that Overture used a first price auction to sell internet advertising. And it turned out they got these crazy dynamics where people were writing bidding bots basically that would go and be constantly updating their bid prices for advertising. And these bots would be chasing each other around in prices, and prices would be constantly sort of oscillating throughout the day as everyone tried to get the lowest price. So a nice thing from a systems perspective is that strategyproofness sort of allows you to have some stability in what people are going to want to report. And then from sort of evaluating sort of questions about how good is this approach, if we want to ask, what is efficiency going to look like, or what is revenue going to look like, if we're using a strategy proof auction, we can just assume that people report their true valuation because we know it's optimal, and then ask those questions. If you want to design some non-strategy proof auction, you either have to go through and do the analysis to figure out what people ought to bid, and then hope that people really will in practice find that, or if you don't do that analysis, you're likely going to get wrong answers about what efficiency and revenue are going to look like. There are questions on why we want to go with the strategy proof auction?
Those things might all be worth putting up with. You've got a lot more money out of it.
Right. Yeah. So there's definitely the pushback.
Sort of fourth benefit.
Right. Here, right. So and that's one of the things. So that's definitely a concern. Something that, for example, the auctions that sell internet advertising are typically not strategy proof in most cases. Although actually Facebook does use a strategy proof auction. But right. So certainly there might be reason to abandon it. But this is why, at least in this work, we went with that approach. Right, and so actually we also have a nice recipe for designing auctions that have that satisfy this property, and it dates back to some work by Myerson in the economics literature. And basically the way it works is you design an auction where you ask a bidder for his valuation, and then you decide how to allocate the goods in question using a monotone rule, where monotone here means if you report a higher valuation, you should get more of the goods you're interested in. Or in our setting, if you say you have a higher valuation, you should get more of your demand satisfied. And then you charge him in a particular way that's basically a generalization of the second price rule from before. And so right, a simple observation is that if we didn't have sharing involved in the picture, then the greedy algorithm we're using would be monotone. Right? If everyone is getting exclusive access, then if you report a higher value, we're going to consider you earlier in the greedy algorithm. So there will have been fewer people allocated at that time, so we're more likely to be able to accommodate you. So if we didn't want to allow sharing, we'd basically be done right here. As far as designing the auction, we just have to sort of apply the rest of the Myerson recipe, and that tells us exactly how to charge prices.
Wait a minute, I did that one a little faster. So you're saying, with no sharing greedy is monotone, but then you just said a bunch of other things about. So you're suggesting that you could actually have kind of a strategy-proof implementation of greedy by asking vertices to report their value.
Right. So forming the claim is if your allocation rule for deciding who gets the goods at the end of the auction is the greedy rule, then if you ask people to report them and then you use that allocation rule and then you charge prices according to Myerson's formula, then the outcome is going to be a strategy-proof auction. And so more generally, it's sort of from an algorithmic perspective, basically, if you can find such a monotone allocation algorithm.
So this is implicit in Myerson's work. Do you go back a slide for this?
Yeah. It's you might know.
In other words, that second bullet there is any monotone rule.
Any monotone rule.
I see.
Yeah, it's implicit in there, right? So I guess Archer and Tardosh rediscovered it in sort of the term for applying approximation algorithms. But basically, it turns out that they were basically using Myerson's work on optimal auction design. It's sort of the same insight he used there.
And greedy with sharing is not monotone?
Yep, I'll show you why. So suppose we have two people out there, and we have two channels we can allocate people on. And suppose node A can use channels 1 and 2, and node B can only use channel 1. So if B is the higher bidder, we're going to consider him first, then assign him to channel 1, and then when we consider A, we'll say, great, we can give you your own channel and put you on channel 2. Everyone's going to be happy, everyone's going to have his own channel. So now suppose A is a higher bidder, and we consider him first, and we're just operating greedily, so we'll have some sort of rule for assigning him to a channel, and maybe that rule is take the lower numbered channel and assign him there. So we assign him to channel 1, and then later, sometime later when we come back and think about B, we'll say, the only place we can assign you is channel 1. Well, it looks like sharing is going to be better than not assigning you at all, so you're going to share with A on channel 1. Right? And so now we've violated this monotonicity because A reported a higher valuation, but he ended up with less. He originally had a channel to himself, and now he has to share a channel. Right? So because of these externalities, the greedy algorithm is no longer monotone.
Is it really externalities or the fact that there's a tie for utility in the allocation of the first channel to A? You see what I mean?
I think if you only have a single channel, then I don't think you can. I think you might be okay if you're only auctioning off a single channel. All of the examples I know where bad things happen require multiple channels and some rule where you make a decision and it later turns out to have been the wrong decision, like this.
But I guess what I'm saying is that the source of the difficulty here, right, is not really the sharing per se. Mm-hmm. It's that there was a tie. In the first greedy step, there was sort of a tie in the utility in assigning channel 1 or 2 to A.
Right.
And it turns out that in the next step, you see...
Yeah, well, even if it was not a tie, right? Maybe we assigned channel 1 because it was slightly better, because maybe for signal reasons, channel 1 is slightly better. But it turns out that A would rather have a channel to himself than have a slightly better channel shared. So you can get the same result here, even if the values of the channels are not exactly identical. Okay, right. So we need to do some things algorithmically to make the greedy algorithm monotone. And I'm not going to go too much into the details, but I'll basically just say at a high level we do two things. One's we do called bucketing. If you know about ironing in the economic sense, you can think about it as ironing the input valuation functions. And basically what it means is we're going to coarsen the space of bids. So maybe we'll treat bids between $11 and $20 as just as if you had bid $11. We're sort of going to throw everyone that bid in that range into the same bucket and treat them identically. And we're only actually going to allow sharing within a particular bucket. So sort of the size of the bucket gives you a knob that sorts of trade-offs between how good use of information you have about people's valuations and how much sharing you're going to allow. It turns out this isn't quite enough to guarantee monotonicity, And occasionally we need to do something where we cancel people's allocations at the end, which we call output ironing. And if you could think about it in the previous example, if we just went back and said up at the end, oop, we violated monotonicity when we were doing this. Sorry, B, we're just kicking you off and not giving you a channel at all. And that way A gets a channel to himself and we haven't violated monotonicity. If we do that, and that's going to do it. Of course, it's also inefficient, right? We had this allocation we liked that had higher social welfare, and we're giving up some of it to get this strategy proofness property. And this might be hurting our revenue, so we might not want to do it. And so one of the things we will look at is how much this hurts us.
So bucketing can't possibly work, can it? If I just multiply all bids by 10, suddenly the buckets have all gone away.
Right. So you would So the bucket size you would choose to use sort of depends on the range in which people you think are going to be bidding, and it is something you sort of have to tune to the parameters.
But bucketing will always reduce social welfare, right? The only problem is without bucketing, you might never get to a true valuation, so you can't make an optimal assignment.
Right. So bucketing is throwing away useful information for the optimization problem, right? So it's going
It must
to
reduce welfare, right?
well, since we're not solving optimally, there's right. But yeah, I agree that the intuition is that it should reduce
There's
welfare.
a chance we stumble into a better local solution. That's good.
Yeah.
So overall, you don't care about social welfare, only about truthful.
No, I do care about social welfare,
That's
but I don't know how to. So this goes back to one of the nice things about strategy proofness I said earlier. I don't have a good way of doing the analysis of figuring out how people should bid if I use something that's not strategy proof in this auction. So I can't give you a meaningful guarantee about what social welfare is going to look like because I don't know how people will bid into the auction. So I could make the optimistic assumption that people just tell me their true values, and I could say, yep, my social welfare is great, and there actually are papers that have done this. But in some sense, that's not a fair comparison because those are not the, I'm going to be solving an optimization problem better, but with the wrong inputs. And whether that's better or not in practice is something.
But you cannot solve both, or your basic problem is to make it strategy proof.
Right. So what we were looking at was from an auction design perspective how we can make it strategy proof, and we did quite a few simulations to evaluate what we were doing. Although our point of comparison is Veritas, which is a strategy proof algorithm. So what this shows is for varying numbers of participants in the auction, and what we did is we took a city and we scattered people with heterogeneous preferences for spectrum across that city according to population density. And then we did propagation modeling to figure out who it was that would conflict, and then from that we made a conflict graph. And so once we had this conflict graph, we could then try different auction algorithms on that conflict graph. So we had different numbers of participants in the auction, and then we're reporting the percent change in social welfare relative to the baseline of the Veritas algorithm, which is another strategy proof algorithm but does not allow sharing. And so you can see that sort of with small numbers of people, there's actually not much need for sharing. So we're hurt a little bit because of these things we do with bucket ironing. But then as we get more and more people involved, there's more and more meaningful opportunities to share. And so, sort of these, at least sort of with the range of parameters we looked at, when there's a lot of people involved, we were able to get about 40% more social welfare from sharing. So that's at least promising that there seems to be some gain, and it's worth looking further into accommodating sharing.
There's no bound on how far off any of these are from true optimal.
Right. So the closest thing we have to an upper bound is this greedy, which is here we just ran the greedy. We just said suppose the greedy algorithm knew the true inputs, and we just ran the greedy algorithm. How good would you do? So it is still not optimal because we can't solve the problem optimally. But it shows that we're sort of 10% off from that upper bound of what you would get if you got a non-strategy proof. So whether that loss from strategy proofness is going to make up for the getting better information, I don't know.
So it's a simulation, right? So this assumes that people would actually bid their value.
Right. So in particular, and because we're running a strategy proof algorithm, that's a fair assumption to make, because we can promise them it's going to be optimal for them to do so, right? In this, it's sort of an upper bound because we don't actually know what people would bid in this round, but it does provide, it does let us ask how much we're losing.
So the network structure, how did you get the network structure with the conflict graph?
Right. So we randomly sort of scattered people on a city, and then we actually did Longley Rice propagation modeling. So we looked at the terrain and basically computed who would interfere with each other based on some interference threshold that we chose.
Has there been any work on actually looking at conflict graphs in the real world?
Yeah, there certainly has been a lot of work, and there are definitely complaints about conflict graphs, right? It definitely is an approximation to reality, but it's at least a useful approximation as a starting point.
I mean, if the graph has low tree width, then sort of you can do more optimal things than the greedy approach, right?
Yeah, potentially. So I guess one of the things that got asked earlier is revenue, and I don't want to spend too much time dwelling on it, but so this is the same thing. So the purple line here is the Veritas baseline, what you would get. And the blue line is our algorithm, and you'll notice that with high numbers of agents, we're sort of slightly better than Veritas, so the sharing is giving us a little more revenue and a lot more social welfare. At the low end, our revenue is sort of minus 100%, and this turns out to be because we're using sort of this strategy-proof second price framework where because we can basically allocate everyone with sharing, then the second price for all of them is 0, so we can't extract any revenue from them. So a standard trick to do in this case, if you care about revenue, is to introduce a minimum bid or a reserve price. And so that shows you the top two lines for the two algorithms. You can see once you do that, our revenue looks roughly similar or slightly better than Veritas again.
That's not strategy proof, right?
That's not
That's no longer strategy.
No, it is strategy proof. You think of it that there's a
You
minimum.
do the same thing even with a reserve.
Right. So right, you can think of it as if you just report your type and it's below the reserve, sorry, you're not getting allocated.
But you are destroying social welfare with the reserve, right?
You are destroying social welfare, and we have some graphs in the paper about the trade-off, and it turns out that the price we chose for this graph, you sacrifice a little social welfare, but not a huge amount.
So can you say again, why are you so much worse with 100 agents, but you still get a set? Why is the
Because basically, with sharing, without sharing, there's competition, so you can get money from people. With sharing, there's no competition.
They don't get to share.
Everyone gets allocated, so you don't have any threat, basically.
So in these graphs, I think you have only one neighbor, and that's why.
You have a decent number of neighbors, but there's also multiple channels in the simulations we were doing. And the details for all of the parameters are in the paper. So I do want to sort of move on. So just to recap this portion of the talk briefly, so we have some evidence that sharing channels increases efficiency in these sorts of auctions, and it's something that we should keep in mind going forward, that we shouldn't just think in this exclusive access paradigm. And sort of a high level thing that incentives matter for designing systems, right? If we didn't think about what the incentives of what people were going to port in our auction, we might well have gotten wrong answers about how good various approaches are. So now I'm going to switch gears a little bit and talk about sort of a different area, and that's peer production. So what peer production is some sort of project where you get lots of people coming together to produce someone. And so, a classic example of this is Wikipedia, right? You get a huge number of people together. They all do lots of bits and pieces of editing, and out pops a reasonably good encyclopedia at the end. One I really like is this, which is known as North Korea Uncovered. And it's basically a bunch of people who had been to North Korea or had some other source of information, just started labeling points of interest in what's ordinarily a very secretive country. And so the end result is actually a hugely detailed map of all sorts of points of interest in North Korea. And so one thing that I view as peer production that might be somewhat non-obvious is I view sort of peer-to-peer file sharing as a form of peer production, right? You have a bunch of people that are all sort of doing work for each other, and the production at the end is files that people want. They're sort of giving files to each other. And so one thing we looked at is BitTorrent, which, depending on exactly what measurement you look at, accounts for something like 1/3 of the traffic on the internet. So it's a huge chunk of traffic, and I said it's being used for file sharing. So people are using it to get movies and TV shows and music and things like that. And so there are some sorts of broad general interest communities that are sort of open to the public where you can sort of get anything you want. And there are also a large number, about 800 or so, of more private communities where you have to sort of become a member in some fashion. You'll have a login so they can track you. And they tend to be clustered around a particular interest. So one community we took a look at called Dime is built around the trading of live concert recordings. So if you want to see the Marvelous Toy Show in Los Angeles, if you want to hear the recording of that, or the Ani DeFranco concert from Toronto, Ontario, you're unlikely to have been able to go to both of those shows, but you can get recordings of both of them through this site. And so there's a large community of about 110,000 people, and it turns out because they have user accounts, they run the servers that you use to access the system. They're able to gather sort of quite a lot of data, and they make it available. Sort of, they have it in a database, and they make it available in reports on their website. So you can ask, for example, you can ask about a user, how much he's uploaded, how much he's downloaded, for all of 110,000 users. So we have about a year worth of data where I went through and scraped daily the pages of all of these users.
So it's hosted, not peer-to-peer, this one?
So there's a host that keeps track of sort of all the metadata, like how do I join a particular file. All the transfer are peer-to-peer. Right, so there's relatively...
Like something like Kazaa, but with sort of centralized bookkeeping.
Exactly. Right, BitTorrent is decentralized, but you need somebody to tell you where to start. And you can also get similar reports for torrents, so we have longitudinal traces of individual torrents as well as snapshots of all of the torrents in the system collected over the course of that year. Right, so just before we go into more detail, to sort of answer some of these questions, the basics of how BitTorrent works in this sense. So a new file or torrent is going to get posted on this site, and then that's going to have include the location of the tracker, which is basically a server that says, okay, I'd like to download this file. Please tell me who else is interested in it so I can find them. And then the original person who posted it is going to act as a seeder and upload that file to anyone who comes along and is interested in it. And these people are known as leechers, and they're the people that want to download it. And so the BitTorrent protocol, one of the nice things it did when the innovations was introduced, is it gives you incentives to upload while you're downloading. Basically, you'll get better performance if you're uploading others while you're downloading, and sort of helps keep the peer-to-peer nature of the system operating. On the other hand, when your download is complete, you can choose to stick around and become a seeder and give pieces of the file to the others, but nothing requires you to do so in the BitTorrent protocol, and there's no real incentive to do so in public torrents, so you'll often find cases where there might be a couple seeders and a huge number of leechers, and torrents eventually die because they run out of seeders and there's no longer a complete copy of the file floating around. So one thing many of these private communities have done is they've come up with various ways to provide incentives for people to stick around and seed files after they've finished. So a popular one is known as share ratio enforcement. And the way it works is that it's a limit on the ratio of the amount you upload to the amount you download. For example, in this system, you must upload 25% of the bytes that you download. Or the way we view this in the alternative is, essentially they've introduced money. You get paid $1 every time you pay $1 every time you download a byte, and you get paid $4 every time you upload a byte. And there's sort of been a lot of work looking at these. Most of them has looked at them sort of as systems asking, how does the number of seeders compare between public and private communities and things like that. Ours is sort of the first study where we've gone and looked at a large trace as an economy. And so the broadly question we're interested in is how can we increase efficiency in these sorts of systems? And there's all sorts of complicating factors. People have heterogeneous connections, heterogeneous preferences. There's a long tail of files. We have to worry about these incentives and rationality. People free ride. So sort of a lot of things going on. So this is sort of a histogram of share ratios in the system. And you can see there's sort of a broad spectrum of people all the way from a big pool of people who have a ratio of 0, that is they've uploaded nothing. So these are the free riders who are just showing up and taking resources and are eventually going to get kicked out for not having contributed anything. On the other side, you see some very altruistic people that are sort of uploaded 3 times as much as they've downloaded at the very least. And so this is, this is 12 times what they're required to do to stay in the system. So there's clearly people out there that are willing to contribute quite a bit. And then, so they go down, there's a bump here around 2.25 of people doing the minimum. And there's another bump here around 1.0 of people maybe who are trying to give back as much as they take, sort of contributing their share, perhaps, in their mind. So there's sort of this large difference in how people use the system, including people who are willing and trying to contribute quite a bit. And as you might expect, this in contrast to public systems where there are relatively few seeders, here there is a huge number of seeders. It's not uncommon to find files that have 30 or 40 people seeding and a single person downloading them. So when you do download in this system, you get really fast performance. You have lots of people that are just throwing pieces of the file at you. So basically, you can download it as fast as your connection is going to allow you. The flip side of this is, right, you need to earn money to stay active in the system. So if there's lots of people trying to seed at any given time, there's a lot of competition to earn money. Right? So figuring out how you can earn money and stay in the system is something that's important for you as a user, and both sort of anecdotally on the site's forums and in an interview with the moderators, this clearly is something that people care about. So there's a lot of obvious things that are going to do it, right? If you have more bandwidth, you're going to be able to throw pieces at people faster. So you're going to get a higher upload rate on a particular file, and if you stay there longer, you're going to upload more. Perhaps one less obvious thing is that there's a huge difference in the upload rate you get sitting on a file as the age of the file changes. So early on, you can basically upload as fast as your connection is going to allow you. And then after a few days, it's gotten pretty low, and there's this long tail where there's not much opportunity to earn money. So in some sense, there's this interesting dynamic where if you join a file early, it's free in some sense, because you can earn all the money back and then some by reselling it to other people. If you join a file late, though, it's almost entirely cost to you. You would have to sit there for a really long time in order to earn back the amount you spent to get the file. And so, teasing apart both factors, so each of these lines shows the amount you get for a particular age of the file at different bandwidths. So each line is an age, and each point is a bandwidth. As you can see, it does increase with bandwidths, but age is a huge factor, right? So if you're down here with 50 kbps on a very new file, then you're uploading at the same rate as somebody with a 300 kbps connection who joined the file a little bit later. So joining early has a huge effect on how much you're going to be able to learn. And so we had an interesting natural experiment during the time we were doing our study. We were tracking how many active downloads there are at any given time, and it turns out to be about 4,000, varies somewhat depending on the time of the day. I know these were sort of evenly split between new files, less than 2 weeks old, and old files that are more than 2 weeks old, despite the fact that new files are a very small percentage of the total files available in the system. They make up half the active downloads at any given time. And then over the Christmas holiday, there was a few days where they announced a free Leech period. And so what this meant was downloading was free. You didn't get charged for it, but you still got credit for uploading. So as you might expect, right, this caused a huge surge in interest in people downloading things. Right? They no longer had to pay for them, so they were getting everything they could while they could do so. Interestingly, though, you notice this black line, which is the new files, didn't really budge at all. So people were already downloading everything they were interested in this type of file. The old files, though, shot up tremendously and account for basically all of the gain. And if you look at sort of very old files that are more than 2 months old, the jump was even more pronounced. And so clearly there's this sort of pool of old files that people would like, but they're not requesting because in some sense they're too expensive. Right? There's not this opportunity to earn money by selling them back. And interestingly, we also looked at the number of seeders over this time period, the number of people that were doing all of this work, and that number was unchanged. Right? So not only is there this group of people who would like to be downloading more than they actually are, we actually know there's capacity to serve them because they successfully did so with the same number of people standing around and doing the work. Right, so this points to there's definitely this, this inefficiency in the system that we could think about trying to rectify. Right, so sort of, things we found from our measurement study, and it's something we're still working on. It's still in relatively early stages. Right, we found that torrent age has a major effect on the demand and the effective cost down the file because of the option to then turn around and sell it to people. And there's significant unused capacity in the system, and there's also people that would like to make use of that capacity if they could. So from an algorithmic perspective, one thing we'd like to say is, how can we price, change the price of these older torrents in some principled way to encourage people to take advantage of these older files. Another interesting question we'd like to try to figure out, this community uses 0.25 as their required ratio. Other communities choose different numbers. What is the optimal number to choose for these communities? Questions on this study? Okay, then I'll spend, I guess, a couple minutes at the end until I run out of time talking about some of the other research directions that I'm interested in pursuing. So there's been a lot of work on prediction markets, which are sort of, you can think of them as stock markets where you can bet and predict what is the probability that somebody's going to win this weekend's football game or is going to win an upcoming election. So there's been a lot of work showing that these are, you can get good predictions out of these sorts of markets if you're just sort of interested in knowing sorts of exogenous events out there in the world. There's also a lot of interest in using these markets for sort of internal decision making by companies. For example, is the software going to ship on time? Or if I'm a TV executive, or a movie executive, what movie should I produce? And in many of these, right, when you want to start making decisions with the markets, it turns out that the nice incentive properties no longer apply, and people actually start having incentives to ruin the information your markets are giving you in order to produce money. So one thing I'm interested in doing is thinking, I've done some work, and I think there's still a lot of open questions I'd like to push more on how we can really build these sorts of prediction markets, but for decision making. A sort of related issue comes in with something like evaluating programmers, right? So you might have a whole bunch of programmers doing a whole bunch of different tasks, and you might want to do two things. One, you might want to evaluate them about how fast they work and encourage them to work hard and quickly on tasks, so you know how well they're doing in that metric. You'd also like some information about how long various tasks are going to take in order to be able to figure out how many programmers you need to be employing, for example. So each of these problems in isolation is fairly well understood. If you want to encourage somebody to work efficiently, this is known as a principal agent problem in economics, and there's a whole literature on these. If you want to just figure out how long something's going to take, well, then you're back in this prediction market or scoring rule type setting. Interestingly, there hasn't been much at all done at the intersection. I think there's an area ripe for work. I've talked about sort of markets that come out of systems of one sort or another in this talk. I'm also interested in matching markets. So these are the markets like the ones that match school children to schools. Another very important matching market are matching markets for organ transplants, in particular for matching kidney donors and patients. And there's been a lot of work on these, but in a very simple model where you sort of assume that there's some pool of donors and patients and you want to match them up in some fashion, and it's a static one-shot thing. In reality, there's a lot of interesting dynamic problems that haven't been touched to the same extent. For example, in reality, there's new people coming into this market over time. And so just taking the most matches we can right now might not be the best thing. We might be taking worse matches than we could if we were willing to wait a little while, or we might be able to get more matches overall. So I think it's an interesting online stochastic optimization problem. There's also issues that in these markets, we have some idea of how good a match is, but in reality, after a match is created, tests have to be done, and then you find out whether it was actually people were compatible, or they have to sort of go back in the pool and wait some more. And so currently, sort of the existing algorithms don't think about this at all. I think there's room to sort of think about these issues as part of the matching process. And I'm also interested in questions of sort of fair resource allocation. So this has applications, for example, in a cloud computing setting, right, there might be a bunch of different resources out there, and you have a bunch of users who all run on different sorts of tasks, and you want to somehow give them their fair share of this bundle of resources. This is something that, for example, Scott Schenker has been looking at a little bit lately. There are also applications in other areas, for example, air travel. When bad weather strikes, basically airlines have to go out and allocate delays to people, and here delays are a resource you don't want to have. And it turns out they use a very simple algorithm for doing this, and it seems like there's a lot of room for improving the way we respond to weather delays in air travel by thinking about the different algorithms for assigning these. So thank you.
Actually, a very interesting talk. I think since we've had lots of questions during the talk and time's come to an end, we'll